Welcome to video 13.1 for a discussion of first row D block elements, the transition metals. My kind of music. Accessing prior knowledge, it will be helpful to remember electron configuration and the exceptions of chromium and copper. It'll be helpful to remember the idea of a coordinate bond, a bond formed when the pair of electrons in a chemical bond are donated by one atom. Helpful to remember some molecular shapes, such as linear, tetrahedral, and octahedral. And helpful to remember the idea of oxidation state and charge on a simple level. We'll do more on oxidation state in topic 9 when we study oxidation and reduction. But generally speaking, for a metal, the charge on the ion is roughly equivalent to the oxidation state. And that's a good working definition for now. The big idea, the transition elements have characteristic properties. These properties are related to their all having incomplete D sublevels. And the relationship to electron configuration becomes very apparent with that statement. First understanding is some of the different concepts or properties of these transition elements. First of all, the first row D block elements have similar physical and chemical properties. Starting with scandium, notice that they have relatively similar atomic radii. And that similarity in atomic radii will be an important cause of their similar physical and chemical properties. So why do they have similar radii? Well, let's look at their electron configurations. They're all adding electrons to the 3D. They all have 4s2. So scandium has 21 electrons. It has 19 core electrons. Those are the 19 core electrons, so 21 protons. That means it has a Z effective of approximately +2. Argon has 28 core protons, 30 electrons, 30 protons, so that means it has a Z effective of approximately +2. So the effective nuclear charge is not changing very much as I go across period 3 in terms of the transition metals from scandium to zinc. That leads to similar radii, which means they can form alloys quite easily because similar size atoms in the metallic bonding structure can be replaced. Transition metals also have high electrical and thermal conductivity, and that relates to their sea of electrons and their metallic bonding. They tend to have a high melting point because they all have a relatively small atomic radius with larger charged ions, and that leads to stronger metallic bonding, which leads to higher melting point. They are malleable, which as we know is a characteristic of metallic bonding, same with being ductile. They have a high tensile strength, and the word tensile, what the heck does that mean? I'm not even sure if I know the exact definition, but what I know is that they can hold large loads without breaking. Titanium is a very common, sort of just think in your head about a light transition metal that's strong, and you think titanium. We're going to talk about magnetism later, but iron, cobalt, and nickel are ferromagnetic. We'll talk about that a little bit later. Transition elements form compounds with more than one oxidation number or more than one oxidation state. We'll talk about that a little bit more too. They form a variety of complex ions. They form colored complexes. We'll notice a number of different colors. They act as catalysts for many reactions. Transition metals have atoms with an incomplete D subshell, or they can give rise to cations with an incomplete D subshell. Can you think of any D block elements that don't fit this definition? There's one. That element is zinc. Zinc is not considered to be a transition element as it does not form ions with incomplete D subshells. Zinc is argon 4s2 3d10, and so this is full. The D shell is full. When it forms an ion, it tends to form the 2 plus ion, so that means it is argon 3d10, so the D subshell is still full. So zinc is not considered a transition element. Transition elements can have variable charge, but the 2 plus ion is the most common, and that is with the 4s electrons removed first. These variable charges for transition metals come from the fact that the 3d and 4s electrons have relatively similar energies. So if I remove a 4s electron and then I remove another 4s electron from titanium, the next electron removed will be a 3d electron, and that's not a very large jump. And then there's another 3d electron before there's finally a large jump up to a 3p electron. Calcium, on the other hand, if I remove calcium's 4s electrons, the large jump occurs for that third electron, which is a 3p electron. So calcium forms 2 plus. But because titanium has relatively similar small jumps in ionization energy, titanium can form 2 plus, 3 plus, and 4 plus oxidation states because of the close successive ionization energies. This is a table with more common oxidation numbers found in blue. Copper can be +2 or +1 as the most common oxidation states. All of them can be 2 plus or +2. And remember that zinc, sorry about that. Remember that zinc is not a transition metal by definition. From our data booklet, this is looking at atomic and ionic radii. The ionic radii for some of the different charges for transition metals is given in the data booklet. We also have this table in our data booklet of the common oxidation numbers for the 3D ions. This is table 14. So this is another helpful table in your data booklet. So all transition metals show both 2 plus or +2 and +3 oxidation states. And the 3 plus ion is a stable state for elements from scandium to chromium. The 2 plus is more common for the later elements after chromium, and the increased nuclear charge of the later elements makes it more difficult to remove the third electron. So even though it's possible, it's not as likely with the larger elements. Maximum oxidation state of the elements increases in steps of +1 until a maximum of 7 for manganese, and that manganese is argon 4s2 3d5. If it loses all 7 electrons, it ends up with a +7 oxidation state. After that, the maximum oxidation state decreases in steps of 1. You're not going to lose as many of the d electrons because some of them end up paired and being more stable. Oxidation states above +3 generally show some covalent character, and this is sort of that continuum between completely nonpolar and sort of being 100% ionic. The reality is most bonds are somewhere in this continuum. So oxidation states higher than +3 generally show some covalent character because the metal ion can actually distort the electrons of a negative ion and create some covalent character. Compounds with higher oxidation states tend to be oxidizing agents, like the use of potassium dichromate, K2Cr2O7, in the oxidation of alcohols, which we'll talk about in organic. Transition metal ions have a high charge density, and that attracts water molecules and other ligands, which form coordinate bonds with the positive ions to form a complex ion. So the transition metal attracts water molecules. The idea of a ligand is something that has it's either an ion or a compound that has a lone pair that can form a dative bond or a coordinate bond. So these ligands are attracted to the metal because it has such a high charge density, and it forms these complex ions. So here is in brackets, we would give this a 3 plus charge, this iron ion complex with water. The surrounding molecules or ions are called ligands, and the ligands must have a lone pair in order to form the coordinate bond. So these are sometimes called coordination complexes because the coordinate bonds around the metal ion. The number of coordinate bonds from the ligands to the central ion is called the coordination number. So if there are two ligands that form two coordinate bonds, that would be a coordination number of 2. 4 ligands can form a square planar or a tetrahedral shape. If there are 4 coordinate bonds, that's a coordination number of 4. If it's octahedral in shape and there are 6 coordinate bonds, that's a coordination number of 6. This is approximately similar to AX6, approximately similar to AX4, and related to AX2. So we can use some of our prior knowledge to understand these shapes. Number of different complex ions here and the number of different ligands and the coordination number. Look at the coordination number of 6 if there are 6 water molecules. If there are 4 chloride ions, that's a coordination number of 4. The oxidation number of the central ion can be deduced if I know that chloride, for example, is 1 minus, and there's a total, that's 4 minus, and the total charge is 2 minus. This copper must be 2 plus. So I can do a little bit of algebra to determine the oxidation number of the center ion. Transition metals have huge economic importance in terms of catalytic activity. Just a couple simple examples. The Haber process is the use of nitrogen and hydrogen to form ammonia. This is an incredibly important reaction. During World War II, it provided fertilizer to grow food and also for explosives, nitrogen compounds for explosives. So there's a fair amount of controversy is maybe not exactly the right word, but there's a fair amount of discussion that goes on about Mr. Haber, Fritz Haber, and his development of this reaction. A vanadium oxide complex is used in the compound is used in the contact process, which makes sulfur trioxide, which is used to make sulfuric acid. And sulfuric acid is a hugely important chemical in industry. Homogeneous catalyst is a catalyst that's in the same state as the reactants. For example, the iron 2 plus in heme carries the oxygen and carbon dioxide that's transported through the bloodstream. I'm not sure if I'd call that a catalyst, but certainly it's an important use of iron as a transition metal in our bodies. Cobalt forms an octahedral complex with cobalt in the center of vitamin B12, and that 5 sites are occupied by nitrogen atoms, and the 6th site is used for biological activity. And in that case, it is a bit of a catalyst. Magnetism is an interesting discussion. The property of all materials is diamagnetism, and it produces a very weak opposition to an applied magnetic field. Essentially, there's no effect from a magnet. Diamagnetism is essentially no effect from a magnet. That's kind of what I'm saying there. Paramagnetism occurs in substances which have unpaired electrons. It is stronger than diamagnetism, and substances exhibit magnetic behavior in the presence of a magnet if they are paramagnetic. Ferromagnetism is when a substance retains its magnetism after it has been removed from an external magnetic field. Ferromagnets, we're familiar with iron having ferromagnetic properties. Diamagnetic is an example like silicon. All spins are paired. If it's sp3 bonded, sodium chloride, the sodium ions and the chloride ions, all the electrons are paired. Paramagnetic, something like iron, that has some unpaired d electrons. Even in its ionic form, when the 4s electrons are removed, there are still unpaired electrons. And those unpaired electrons means that this iron will react to the presence of a magnetic field. So let's think about oxygen. Oxygen is 1s2, 2s2, 2p4. So there are some unpaired electrons. And if you have a relatively strong magnet here, and you pour liquid oxygen between the magnets, they will actually be held in space by these magnets. It's a really cool demonstration I've seen it, majority of my life I've seen it on video. I've only ever seen it in person once when I was in college. It is really neat. Pouring liquid oxygen, these unpaired electrons respond to the magnets and it can be held in place. Ferromagnetism, iron, cobalt, and nickel are ferromagnetic, and if the particles are arranged randomly and the little magnetic fields are arranged randomly, it's just a paramagnet, if you will. It has paramagnetic properties. But in order to be ferromagnetic, all of these fields have to be aligned. So a piece of iron, if you run a magnet over a piece of iron multiple times to try to align the magnetic fields of all the atoms, it will end up as a ferromagnet, a permanent magnet. I think of ferromagnetism as permanent magnetism. International mindedness, transition metals are hugely important in many places around the world. Connections to other topics, lots of connections, including coordinate bonds from topic 4. In terms of a summary, what I've got for you is transition metals exhibit many unique properties, many of which are due to their electron configurations. So we have an incomplete d subshell in the atoms or the ions. We have a 2+ ion as one of the ions possible. We have multiple oxidation states. We have catalytic activity. And we have colored complexes. The colored complexes will be the focus of 13.2. It's quite an interesting discussion, actually. All right, let's do a couple checkpoint questions. First question, what are the charges on each of the complex ions? A little bit of algebra. Pause the video. See what you got. And the correct answer is D is the correct answer. We're looking for the charge on the complex ion. What is in brackets? Chloride has a 1- charge and there are 3, so that's a total of 3-, so that means the ion must be 3+. In the second complex, ignore the water, it has no charge. There are 2 chlorides for a total of 2-. That means what is in brackets must be 2+. In the last scenario, ignore the waters, we have 1 chloride for 1-, so that means this complex must be 1+. And those are the answers. One last checkpoint question. Which of the elements is the most paramagnetic? Pause the video, figure it out, come back for an answer. And the answer is D, yet again. So let's look at the 4 elements involved: scandium, titanium, vanadium, and chromium. They all have an increasing number of unpaired electrons. Chromium has the most unpaired electrons of all 3 of these elements. Because it has the highest number of unpaired electrons, it would be the most paramagnetic. And that makes chromium the best choice. Thank you for listening. Hope you have a great day, and I'll see you in class.